In 1963, meteorologist Edward Lorenz restarted a weather simulation from a printed number. On paper, the value was 0.506. But inside the computer, the stored value was 0.506127. That difference was tiny, but the system did not treat it as tiny forever. At first, both simulations followed almost the same path. Then they began to separate. And after enough iterations, they became completely different trajectories. The machine was not broken, and no randomness had been added. The equations were still deterministic. The same update rule was being applied again and again. What changed was the initial state. The Lorenz system is three coupled nonlinear differential equations, originally used as a simplified model of atmospheric convection. At every point in phase space, those equations define a rate of change. So in code, the process is direct. Read the current state. Compute the rate of change. Advance the values by a small time step. Then feed the result into the next iteration. It is a loop over state, using floating point numbers and a numerical integrator. But in a nonlinear system, each output becomes the next input, so small differences are not just preserved. They can be amplified. A rounding difference becomes a state difference. A state difference becomes a path difference. And eventually, the paths no longer describe the same future. This is deterministic chaos. Fixed rules, sensitive initial conditions, and prediction that only works up to a horizon. Now, instead of watching one path, watch 25 initial points evolve under the same equations.